Okay, so in this video we're going to talk about section 4.4 from your book on inverse trig functions. So typically when I lecture in class, of course, I'm writing on the board and that slows me down. So, if you're taking notes on this, of course, feel free to pause or rewind and rewatch things if you miss things, because I'm probably going to go a lot faster today than I typically would in class. So, inverse trig functions then. So, consider the graph of the sine function, the traditional sine function from a high school trig class. We look at this function and we can plainly see that it's not one to one, so it doesn't have an inverse as it stands. But we like to talk about inverse trig functions, so we want to figure out a way to make an inverse. And so we remember from our discussion about inverse functions that we can always restrict the domain of a non-one-to-one function to make it one-to-one and then have an inverse. And so the standard domain to restrict the sine function, we could make lots of choices, but the standard domain to restrict to is the interval between minus pi over 2 and pi over 2. And so if we take and we restrict the sine function to that interval, we look at the graph, it's just the piece of the sine graph between minus pi over 2 and pi over 2. We can see that this restricted function is now one-to-one. It has a domain for the closed interval from minus pi over 2 to pi over 2 and a range from minus 1 to 1. And so this restricted function will now have an inverse. We call this inverse of the restricted sine function the inverse sine function. We will denote the inverse sine function arc sine x, or sometimes you'll see sine to the minus 1 of x. I prefer arc sine x because sine to the minus 1x is a little bit confusing. It kind of almost seems like it could mean 1 over sine or cosecant. And so the arc sine notation doesn't have any of that ambiguity. And thinking about what the inverse means, the arc sine is the angle between minus pi over 2 and pi over 2 because we restricted the domain of the original function whose sine is x. And so remember, we can take the graph of the restricted sine function here and we can reflect it about the line y equals x, and that will give us the graph of arc sine function. And so it has a similar shape, has a similar look, except the concavity has switched in the two quadrants, and the domain of the arc sine function is from minus 1 to 1, and the range is from minus pi over 2 to pi over 2. Okay. So now we want to think about how we would compute the derivative of the inverse sine function. And so we're going to take an approach similar to what we used for finding the derivative of ln. So we start with the fact that the sine of the arc sine of x is equal to x. Okay, and that's just because arc sine is the inverse of sine, and so when you compose the two functions together, you get x. So if we take that equation and we differentiate both sides, and so we're going to use the chain rule here. The derivative of the sine of arc sine of x, it's the derivative of the outer evaluated at the inner times the derivative of the inner. We don't know the derivative of the inner, but the derivative of the outer is cosine. So the derivative of the outer evaluated at the inner is the cosine of arc sine of x times the derivative of arc sine. We don't know that, so we'll just write it as derivative of arc sine. And then on the right-hand side, the derivative of x is equal to 1. Solving for the derivative of arc sine, we get this formula. The derivative of arc sine of x is 1 over the cosine of arc sine of x. Now, that's technically a derivative formula for arc sine of x. The problem is the function cosine of arc sine of x in the denominator is not really familiar to us. And so we want to re-express it in a more familiar form. And so we're going to use some right triangle trig. So if we let theta be arc sine of x, remember arc sine of x is an angle, the angle whose sine is x. So if theta is arc sine of x, or that's another way of saying sine of theta equals x, and so we can draw a right triangle representing that situation. So remember, sine of an angle is opposite over hypotenuse from SOHCAHTOA. And so if the sine of theta is x and we want opposite over hypotenuse to be equal to x, we'll represent it as x over 1. So if we label our right triangle here, the opposite side is x and the hypotenuse is 1. And then we need to use the Pythagorean theorem to figure out the missing side, right? If we call it question mark, we know that x squared plus question mark squared equals 1 squared. And solving for question mark, we get that question mark is square root of 1 minus x squared. So that's the missing side of our right triangle. Okay, so cosine of arc sine of x is the same thing as cosine of theta. Now again, remembering our right triangle trig, cosine is adjacent over hypotenuse. So if we look at our right triangle here, here's the adjacent side, here's the hypotenuse. So we get adjacent over hypotenuse, square root of 1 minus x squared over 1. And so the cosine of theta is, the cosine of arc sine of x is the same thing as square root of 1 minus x squared. So this is a much simpler function to deal with than this cosine of arc sine of x. So if we plug that value that we found up here into our formula, we get the nice following nice simplified derivative formula. The derivative of arc sine of x is 1 over the square root of 1 minus x squared. So that's a good formula. That's an important formula. You want to box that one in. Okay, and so remember, whenever we get a derivative formula, we can always read it back and get a corresponding integral formula. So the integral of dx over square root of 1 minus x squared is arc sine of x. And then, you know how I am, I always like to write it with the u, which is just exactly the same formula. You can choose to do that or not, it's up to you. Okay, and I didn't draw boxes around those two formulas, but you probably want to. Those are important. You want to highlight those in your notes. So let's just do a couple quick examples. The first, we want to just find the derivative of the arc sine of ln of x. This is a chain rule problem. The outer function is arc sine of x, and the inner function is the ln of x. So remember what the chain rule says. The derivative of that composition is the derivative of the outer evaluated at the inner times the derivative of the inner. The derivative of the outer function, that was the formula we just learned. The derivative of arc sine is 1 over the square root of 1 minus x squared, but it's not x squared. We put the inner function in place of x. So we get 1 over the square root of 1 minus ln of x in parentheses squared, and then times the derivative of the inner function. The derivative of ln of x is 1 over x, and we learned that back in section 6.4. Okay, another example I want to do is an integral. So we want to evaluate the integral of x squared over the square root of 1 minus x to the 6th. And we can see our integrals are, our life with integrals is starting to get more complicated as we're learning more techniques. And so here's what we have to think about for this one. So we notice that, excuse me, the original integral is the same thing as the integral of x squared over the square root of 1 minus x cubed, the quantity squared, right? X to the 6th is the same thing as x cubed, the quantity squared. And at first, it might not be clear why we're doing that. But now look what happens. If we let u equal this x cubed right here, which as the problem was originally written, we didn't see an x cubed. We had to do this rewriting first. If we let u equal x cubed, so du is 3x squared dx, or 1/3 du is x squared dx. And so the reason that this approach works is because the x squared dx in the numerator of the original problem, that's basically our du if our u was x cubed. So this is why we had to do that. So if we make this substitution, the original integral becomes the integral of 1/3 du over square root of 1 minus u squared, or we can factor out the 1/3, 1/3 integral of du over square root of 1 minus u squared. And that's our formula we just learned from up at the top of the page here. So that's going to be 1/3 arc sine of u plus c. And then last thing we do is put our u back in terms of x. So the integral of that is 1/3 arc sine of x cubed plus c. Okay, so now we want to do the same thing we did with inverse sine with inverse tangent. We're not going to do it in quite as much detail because we've already seen it once. Right, but we know if we look at the tangent function, it's not 1-to-1, and so we have to restrict the domain. And so if we restrict the domain of tangent to minus pi over 2, strictly less than x, strictly less than pi over 2, that makes a 1-to-1 function, and then that has an inverse. And here's what that restricted function looks like. And you see that minus pi over 2 and pi over 2 are both vertical asymptotes of the function. The tangent of pi over 2 or the tangent of minus pi over 2 is not defined. So the domain is the open interval from minus pi over 2 to pi over 2 because it can't actually take the value of pi over 2 or minus pi over 2. And the range is minus infinity to infinity, right? We hit all the possible y values. So then we can take this function and we can make the inverse of this function. So the inverse of this restricted tangent function is called the inverse tangent function. Makes sense, right? And we use similar notation. We would denote it arc tan of x or tan to the minus 1 of x. Again, arc tan of x is my preferred notation. So that's what I will almost always use. But of course, you have the option. You might, if you're looking at another book, or you're looking, you might see tan to the minus 1 of x. And some of the web work problems might use that notation as well. Okay, and arc tan of x is the angle strictly between minus pi over 2 and pi over 2, whose tangent is x. So again, that's the interpretation of it. And so if we take our restricted tangent function and we reflect the graph about the line y equals x, we get this picture right here. And so that's the arctan function. Its domain is minus pi over 2 to pi over 2, and its range, its domain is minus infinity to infinity, and its range is minus pi over 2 to pi over 2. So just as usual, the domain and range are flipped. Okay, and then as we did with sine, we can, in inverse sine, we can find derivative of inverse tangent. I won't go into the details of that, but I'll just tell you the derivative of arctangent of x winds up being 1 over 1 plus x squared. There's no square root there, and the reason the square root is missing is because the derivative of tangent is secant squared, and so you get a term with a square root in it, but then you square it, so that's where the square root goes away. And then you get corresponding integral formulas by reading that derivative formula backward. The integral of dx over 1 plus x squared is arctan of x plus c, and I write it with the u form as well. Okay, so last thing I want to do is just do a couple of examples. So the first, let's just practice differentiating. So our function we want to differentiate is g of x equals e to the power arctan of x. Again, this is a chain rule problem, just like before. So we want to do the derivative of the outer function evaluated at the inner. The outer function is e to the x. The derivative of e to the x is e to the x. So the derivative of the outer evaluated at the inner is just e to the arctan x. So we recopy the original problem just like we always do. And now we want to multiply that by the derivative of the inner function. The derivative of arctan x is 1 over 1 plus x squared, just from this formula right here. So that's our final derivative of g prime. Okay, and now I want to do an integral problem, and this one's a little bit interesting. And you'll see some problems like this in WebWorks, so I wanted to go into detail for you on this one. So we want to integrate dx over 4 plus x squared. So it looks almost like it should be a du over 1 plus u squared, but it's not quite. Okay, so here's what we have to do. The integral of dx over 4 plus x squared, we can factor a 4 out of the bottom right here. And so if we do that, this becomes the integral of dx over 4 times. Now, if I factor a 4 out of 4, I have 1 left. If I factor a 4 out of x squared, I have x squared over 4, right? Because if these multiply together, they still give me x squared. Okay, that's a little bit unorthodox. You wouldn't typically do something like that, but that works in this case, okay? So now the 4 in the denominator we can pull out as a 1/4. So this is the integral of 1/4 dx over 1 plus x squared over 4. I've just taken and rewritten this. Now if I pull the 1/4 out front as a constant, and I notice that this x squared over 4, I can rewrite as x over 2, the quantity squared. Sorry. Okay, and so if I let u equal x squared over 2, then du is 1/2 dx, or 2 du is equal to dx. So if I substitute those in, my integral, which was in this last form from the previous page, was 1/4 integral of dx over 1 plus x over 2 squared, becomes 1/4, right? The dx is 2 du, so I get 2 du over 1 plus u squared. If I pull that 2 out, I get 2/4 integral of du over 1 plus u squared. And we know that integral, that's one we just learned, that's 1/2 arctan of u, which becomes 1/2 arctan of x over 2. Okay, so that completes the video lecture on 4.4. So you basically know everything you know to do the problems. So there will be some sample problems posted on Moodle and also solutions. And so you can work on those, and feel free to post on the forum during class time or office hours, or send me an email if you have any questions. And also email me or send me an email through WebWork if you're having problems as you're working on the WebWork. So stay safe, everybody, and I'll see you on Wednesday.